right there at the start of my throw, I have the whole mass of the whip moving forward and at a very slow velocity, like my hand is not moving very fast. So the whole mass of the whip is moving forward. And then you can see once I stop the movement of my hand, each successive part of the whip stops. So the actual moving part of the whip gets smaller and smaller and smaller. So as the part of the mass that has velocity keeps getting smaller, the velocity itself has to go up for kinetic energy to be conserved. So eventually you start out with a lot of mass with a slow velocity, and you end up with a very little bit of mass with a lot of velocity.
Gotcha.
It's kinetic energy.
Makes sense.
And then, let's see, kinetic energy. Angular momentum sort of applies, and I'm not sure if it really works out. The idea is that also the whip travels out sort of in this coil, this loop, and they want to say conservation of angular momentum because so you could theorize that, the loop gets smaller as it travels out, just like a figure skater when their arms out, they have more inertia. When they bring the arms in, they speed up. That's sort of the theory of how angular momentum would apply, is that the loop gets smaller as the whip travels out. That one I'm a little bit iffy about. Let's see, centripetal force, I think, would apply there, like when we saw the whip not cracking. Like there, the idea is that and it's really sensitive with the long whip, like a 216-foot whip or whatever, is when you throw the whip out, you need the loop to really travel along itself. You can't have it be like travel like this. In one plane.
Okay.
Out. If it's
in the same plane.
If it's not in the same plane, like this, obviously you can tell like a roller coaster going through a corner.
Sure.
If you go around this way, it's more force on your body. If you go directly in one plane, if you go around the corkscrew that way, it's less force. So the same thing with the whip. The centripetal force kind of applies there, because really, some people try to think, can a whip go like Mach 2? Is there at some point, is it going fast? How fast is it actually going? And why doesn't it crack twice? And part of the deal is, again, related to the centripetal force, is that when the whip comes around, when that loop comes around here, the whip actually cracks right at the end of it, right about here when it's starting to change direction. There's a little arc that the cracker's going to pass through and go flop over like that. At one point it was heading this way, and now it's going to make a real tight turn, and now it's heading this way. And that's pretty much how all whip cracks happen. They happen right before it goes through this extreme amount of acceleration. That'd be like the tightest part of the curve in your roller coaster. So it's going to go boom right around there and then crack. And there's no other point where it's going to change direction like that and go through that kind of acceleration
to
get the crack. So that's kind of why they don't crack twice or 3 times for each throw. And then the wave propagation through strings thing is that you're basically concerned about the speed of the wave that's going through the whip. It more applies when you have both ends fixed, really, like when we were doing that when you were holding the cracker. Is right, directly proportional square root of the tension you have in it, divided by the linear mass density. So linear mass density, right, you can see the whip tapers. So that means the linear mass density is going down as you go through the as the whip tapers down. So that means that the speed of the wave will go up as the whip tapers down. The speed of the wave is going to go up. And then the tension, that can be influenced if you're not even holding the end. You can see you can crack a whip by just like not hit the tree. I can just throw it out there, and like there is tension in the whip. Like just me stopping my hand will put some tension in the whip as it's thrown out. But I can increase the tension by flicking my wrist harder and pulling back on it, putting more tension into it. And you see, it'll give you a slightly harder crack because I'm putting that extra tension into the whip. So that's my basic knowledge of how those 4 physics principles apply to whip cracking.